what two atoms must have if they're isotopes of the same element.
This goes right to the heart of what an isotope is. It's
Right.
like different models of the same car. They might have
Mm,
different features, different add-ons, but they're still fundamentally the same car.
Gotcha. So thinking about those car models, what's the one thing that makes them all part of the same brand?
It's the same with atoms. The number of protons, we call that the atomic number. That's the defining characteristic of an element. It's like the car's make and model, it's the atom's ID card. But just like those cars can have different engine sizes, atoms of the same element can have different numbers of neutrons.
And that's what makes them isotopes.
Exactly.
So the answer to question 1 is 2, the same number of protons and a different number of neutrons. Makes sense.
It's the foundation.
All right, let's move on to question 2. It's all about the weighted average of the atomic masses of naturally occurring isotopes. What do we get from that calculation?
This is where we connect those isotopes to what we see on the periodic table, that weighted average. Taking into account the abundance of each isotope, it gives us the atomic mass of the element.
So it's kind of like factoring in the popularity of each car model when you're figuring out the average price for that whole brand.
Exactly. A good example is chlorine. It has two main isotopes, chlorine-35 and chlorine-37. Chlorine-35, it's more abundant in nature, so it contributes more to that average atomic mass. And you see this on the periodic table. Chlorine's atomic mass is about 35.5, which is closer to the mass of chlorine-35.
So the answer to question 2 is 1, the atomic mass of the element. All right, looking ahead, questions 3 and 4 in both documents,
Yeah.
they seem like repeats of questions 1 and 2.
Yeah, they're probably just emphasizing those fundamental concepts that isotopes share the same number of protons but have different numbers of neutrons, and how that difference directly impacts the atomic mass you see on the periodic table.
Repetition helps it sink in, right?
Yeah, absolutely.
All right, so moving on to question 5, it asks us to describe the protons and neutrons in atoms of two different isotopes of the same element.
We keep going back to that core concept of isotopes.
Yeah.
Same number of protons, different number of neutrons.
So again, the answer is 2, the same number of protons and a different number of neutrons. Okay, question 6 asks, what must be true for all atoms that make up a particular element? What do you think?
This is all about that fundamental identity of an element. No matter what, all atoms of a particular element will always have the same number of protons. That's its atomic number. That's what makes it that element, regardless of how many neutrons it has.
So the answer to question 6 is 2, the same atomic number. Makes sense. Okay, question 7 is focusing specifically on isotopes of carbon. Which statement accurately describes two different isotopes of carbon?
Again, it all comes back to that key difference between isotopes. They have different numbers of neutrons, but always the same atomic number. So the answer here is 3. The isotopes contain a different number of neutrons, but have the same atomic number.
This is making me think about carbon dating. How does that work with isotopes?
Carbon dating relies on the isotope carbon-14. Even though it has a different mass than the more common carbon-12, they both have 6 protons, making them both carbon. And that's how scientists can use it to determine the age of those really old objects.
That's fascinating. Now, question 8 gives us a diagram of different atomic nuclei and asks us 3 questions about them.
This is where being able to understand those visual representations of atoms is really helpful. Let's see what we can figure out from this diagram.
Okay, so question 8.1 asks us to identify the element represented by nucleus 1, which has 9 protons. To answer this, we need our periodic table.
Right, specifically page 9. And if we look for element number 9, we find fluorine. Remember, that atomic number, the number of protons, that's the key to identifying the element.
Got it. Question 8.2 asks us to figure out the mass number of nucleus 2, which is 8 protons and 10 neutrons. How do we do that?
The mass number, that's just the total number of protons and neutrons in the nucleus. So in this case, it would be 18.
Okay, so 8 protons plus 10 neutrons equals a mass number of 18. Last part of question 8 wants to know why nucleus 2 and nucleus 4 are considered isotopes of the same element.
If we look at the diagram, we see both nuclei have 8 protons, which means they are both oxygen. But notice they have different numbers of neutrons. Nucleus 2 has 10, while nucleus 4 has 9.
Ah, so they fit the definition of isotopes perfectly. Same atomic number, different number of neutrons. All right, I think we're ready to dive into some atomic mass calculations.
Let's do it. Now that we've got those basics down, let's look at question 9. We've got a table here showing the atomic mass and the natural abundance of the two naturally occurring isotopes of copper, copper-63 and copper-65. And we need to choose the correct setup to calculate copper's atomic mass.
Okay, so this is where we actually apply that weighted average concept. We can't just like add the atomic masses and divide by 2. We have to consider how much of each isotope exists in nature, right?
Exactly. Think of it like calculating your grade in a class where, say, the final exam is worth more than the quizzes, that more abundant isotope. It's like that final exam, it carries more weight.
Okay, that makes sense. So looking at the answer choices, it seems like the correct setup is 462.93U, 0.6915 plus 64.93U, 0.3085. We take the atomic mass of each isotope, multiply it by its abundance as a decimal, and add those together.
Exactly. That's how we give more weight to the atomic mass of the more abundant isotope, which in this case is copper-63.
Perfect. Our question 10 looks pretty similar, but this time it's about silver, and it's isotope silver 107 and silver 109.
Same principle, just a different element. See if you can figure out the correct setup for calculating the atomic mass of silver.
Okay, so using the same logic, we multiply each isotope's atomic mass by its decimal abundance, and then add those products together. So the correct setup should be 2 106.905U, 51.8%, plus 108.905U, 48.2%.
You got it. Notice this time, though, they give us the abundances as percentages, so we don't have to convert them to decimals beforehand.
Good point. I almost missed that. All right, question 11. This one's about boron and its isotopes, boron 10 and boron 11. Again, we have a table with the atomic mass and natural abundance, but the answer choices, they look a little more complicated.
Yeah, it looks like they're trying to mix things up with the format a bit, but let's break down the correct setup. 1, 10.01U, 19.9, plus 11.01U, 80.100.
Okay, I see what they're doing. Inside brackets, they're multiplying the atomic mass by the abundance, just like we've been doing. But then they're dividing the whole thing by 100. Why is that?
That division by 100, that's just taking care of converting those percentages into decimals. It's basically combining the multiplication and the decimal conversion into one step. The principle of the weighted average is still the same.
Right, right. So whether we convert the percentages beforehand or divide by 100 at the end, we're still ultimately getting that weighted average. Okay, on to question 12. This one's about gallium and its isotopes, gallium-69 and gallium-71.
Think you can spot the correct setup for calculating the atomic mass of gallium?
Let me see. Remembering what we've learned about weighted averages and making sure I'm using those decimals, I think it would be a 1.6086926U plus 0.3989 70.925U.
You got it. You've applied that weighted average concept perfectly there, making sure to use the decimal form of the abundances.
Starting to feel like second nature now. All right. Question 13. This one is about bromine and its isotopes, bromine-79 and bromine-81.
Looking at the table, it seems pretty straightforward. Think you can identify the correct setup for calculating the atomic mass of bromine?
Yep, I think I've got it. It should be 3, 78.92U, 0.58069 plus 80.92U, 0.4931.
Absolutely right. You're a weighted average pro by now. You're multiplying each isotope's atomic mass by its decimal abundance. Adding those results together, you've got it down.
Practice makes perfect, as they say. All right, on to question 14. This one's a bit different. It's about lithium and its isotopes, lithium-6 and lithium-7. But instead of just directly asking for the atomic mass, it's got these 3 sub-questions that kind of build on that information.
Interesting. Let's see what these sub-questions are about. What's the first one?
Okay, so question 14.1 asks us to state the number of electrons in an atom of lithium-7.
This is taking us back to some of those fundamentals of atomic structure. Remember, in a neutral atom, the number of electrons will be equal to the number of protons, and we find the number of protons by using the atomic number.
Right, so if we check the periodic table, lithium's atomic number is 3. So an atom of lithium-7 would also have 3 electrons, since it's neutral.
Spot on. All right, what does sub-question 14.2 ask?
This one asks us to compare the energy of an electron in the first shell of a lithium atom to that of an electron in the second shell of the same atom.
This brings up the idea of electron shells and those energy levels within an atom. Do you remember how the energy of an electron changes as we move further away from the nucleus?
Yeah, if I remember correctly, electrons that are closer to the nucleus, they have lower energy, and their energy increases as they occupy shells that are further away.
That's exactly right. Those electrons in the first shell are held more tightly to that positively charged nucleus. They have lower energy. So the correct answer to question 14.2 is that an electron in the first shell will have lower energy than an electron in the second shell.
Makes sense. Kind of like a ball rolling downhill, the further it rolls, the more potential energy it gains.
Yeah.
Electrons are kind of similar, gaining energy as they move further from the nucleus.
That's a great analogy. All right, and for the final sub-question, 14.3, we're back to familiar ground. It asks us to show the numerical setup for calculating the atomic mass of lithium.
Okay, back to those weighted averages. We need to take the atomic mass of each isotope, multiply it by its decimal abundance, then add those results together. So the correct setup would be 1, 6.015U, 0.0759, plus 7.016U, 0.9241.
Perfect. You successfully navigated all three parts of question 14 there, showing your understanding of isotopes, atomic structure, and those weighted averages.
I'm feeling pretty good about this. It's really amazing how these seemingly simple concepts can be so fundamental to understanding the elements.
Absolutely. And we're not quite done yet. We still have question 15 to tackle, which focuses on silicon and its isotopes.
Bring it on, I'm ready.
Excellent. Question 15, similar to 14, has multiple parts. The first part, 15.1, asks us to compare the energy of an electron in the first shell of a silicon atom to that of an electron in the third shell of the same atom.
Okay, so going back to what we talked about with those electron shells and their energy levels, electrons closer to the nucleus have lower energy, right? So an electron in the first shell of a silicon atom would have lower energy than one in the third shell.
Precisely. You applied the same principle we discussed about electron energy levels, but to a different element this time. Now for the final part, 15.2. We need to show the numerical setup for calculating the atomic mass of silicon, but we've got to consider its three naturally occurring isotopes.
Okay, so this time it's 3 isotopes to consider, but that weighted average concept still applies, right? We just take the atomic mass of each isotope, multiply by its decimal abundance, and then add all 3 products together. So the correct setup would be 1, 27.98U, 0.9222, plus 28.98U, 0.98U, 0.98U, 0.97U, 0.0469.
That's absolutely correct. You flawlessly extended that weighted average concept to deal with those 3 isotopes. You really have demonstrated a strong understanding of how to calculate atomic mass, even when we have multiple isotopes in the mix.
I'm feeling pretty confident in my isotope knowledge now.